Industrial manufacturing requires continuous motion, a toolpath tracing a long, fluid arc, followed by an absolute locked position. Standard direct current motors are built for continuous velocity. You apply voltage and the shaft spins. But if you cut the power, inertia takes over. It is impossible for a standard DC motor to stop at an exact absolute angle without building a complex external sensor loop to tell the motor exactly where its shaft is located. The stepper motor eliminates the need for that external sensor feedback. It provides strict, open-loop precision control. Instead of rotating continuously, it converts a steady stream of electrical current into rigid, fractional degree mechanical movements. The shaft can stop precisely and hold a specific angle indefinitely. Achieving the industry standard rotation of exactly 1.8 degrees per step relies entirely on deliberate mechanical geometric mismatches between the motor's internal stationary and rotating components. By replacing variable electrical feedback loops with strict, absolute physical geometry, engineers created the reliable positioning mechanism that serves as the foundation of modern automation. This diagram illustrates the baseline architecture of a permanent magnet stepper motor. It consists of a diametrically magnetized cylindrical rotor, one half north, the other south, surrounded by a stationary stator containing 4 wire coils. By energizing 2 opposing coils, we create a dominant electromagnetic vector. The permanent magnet rotor immediately snaps to align its poles with these active coils. To control this sequence, the coils are wired to a driver containing an H-bridge circuit. The H-bridge uses electronic switches to reverse the direction of the electrical current. When the current reverses, the coil's magnetic polarity flips, pulling the rotor exactly to the next position. There is a severe spatial limitation to this setup. A 4-coil, 2-pole design creates a massive 90-degree step angle. Physically packing enough wire coils into the stator to reach a 1.8-degree rotational step is geometrically impossible. Relying solely on the magnetic poles of a solid permanent magnet for strict angular resolution reaches a hard physical limit early in the design process. To bypass that resolution limit, engineers developed the variable reluctance motor, discarding the permanent magnet entirely. This diagram demonstrates the principle of minimal reluctance. We have a 6-coil stator surrounding a soft iron rotor. Because iron is highly attracted to magnetic fields, it will physically rotate to close the air gap between its teeth and an active electromagnetic coil. Notice the deliberate geometric mismatch. Using 4 rotor teeth inside 6 stator coils guarantees that all the teeth can never align simultaneously. When one opposing pair is locked perfectly into place, the remaining 2 teeth are forced into an offset position relative to the inactive coils. Sequentially stepping the active phases pulls the nearest unaligned tooth into position. This offset drastically reduces the step angle, tightening the resolution to 30 degrees. This introduces a severe engineering trade-off. Variable reluctance achieves higher resolution, but because the rotor lacks a permanent magnetic field, it loses rigid holding torque. High rotational resolution is functionally useless in manufacturing if the motor lacks the holding torque required to stabilize a heavy mechanical load. The solution is the hybrid stepper motor. It mathematically merges the high holding torque of a permanent magnet with the fine step resolution of variable reluctance. This 3D model isolates the core permanent magnet. Instead of being magnetized diametrically across its width, it is magnetized axially. The North Pole makes up one end of the cylinder, and the South Pole makes up the other. We cap both ends of this magnet with soft iron cups. Each cup has exactly 50 teeth carved into its outer perimeter. This extends the permanent magnetic field, effectively creating a multi-toothed North Pole and a multi-toothed South Pole. Then we introduce the crucial mechanical offset. The teeth on the North Cup are deliberately misaligned from the teeth on the South Cup by exactly 1/2 tooth pitch. This entire rotor assembly is placed inside a stator containing exactly 48 teeth. Placing a 50-tooth rotor inside a 48-tooth stator means only a tiny fraction of the magnetic poles can ever align at a single moment. While a few teeth on the North Cup line up perfectly with the active stator coils, the vast majority remain visibly offset. Reversing the polarities of the stator coils repels the aligned teeth and pulls the specifically misaligned half-pitch teeth on the South Cup precisely into alignment. Because of the 50 to 48 gear ratio and the half-pitch offset, this sequence of pulling offset teeth requires exactly 200 distinct steps to complete a 360-degree revolution. Dividing a 360-degree rotation by those 200 distinct steps equals the industry standard 1.8 degrees per step. The absolute precision of a hybrid stepper motor relies entirely on physical, unalterable gear offsets, rather than variable electrical sensors. While that 1.8-degree mechanical geometry establishes an absolute baseline truth, physical stepping creates sudden stops, jerky movements, and mechanical resonance. This graph plots full-step phase control. It sends raw, binary square-wave electrical pulses to the coils, causing the rotor tooth to snap harshly between positions. Half-stepping smooths this process. By alternating between energizing one phase and then two phases simultaneously, the magnetic field parks the rotor exactly between the physical teeth, doubling the baseline resolution. The ultimate software override is microstepping. This method abandons binary pulses entirely, replacing them with a continuous sine wave current modulation. The current slowly increases in one phase while decreasing in another. These dual offsetting sine waves create a dynamically rotating magnetic vector that pulls the rotor smoothly through the physical gaps. Microstepping functionally erases the harsh physical constraints of the motor, achieving nearly infinite angular resolution and eliminating destructive mechanical vibration. This electromechanical interaction yields visible results on the factory floor, allowing a CNC bit to carve a continuous ribbon of metal from a solid block. The stepper motor merges two disciplines: strict mechanical geometry defining the absolute coordinate system, and fluid software algorithms navigating smoothly through it. It dictates sub-millimeter precision entirely blind, operating without a single feedback loop. By mathematically misaligning metal teeth and subdividing electrical sine waves, engineers built the invisible, highly reliable foundation of the global automation economy.